Hello everybody, this is Mr. Strager once again, and today we're doing part 2 of our 6.1 notes here in Big Ideas Algebra 1. So, we left off last time with 3 more properties that we haven't yet discussed. The reason why I broke these notes up into 2 sections is because these notes are a little bit different than the original day. Our original day's objective was to figure out, first of all, what it means to be a positive or a negative exponent, what it means to be a zero exponent, and how we can combine exponents with the same base. However, today's notes apply to a much broader set of expressions. These rules will apply to any and all expressions. Let's take a closer look. The first one is called the power of a power property. The idea of the power of a power property is this. Let's say we have the expression, let's do 2 to the third raised to the 4th power. Uh-oh. We don't have something as simple as just 2 to the third anymore. Now we have an exponent on top of an exponent. Anytime you have an exponent being taken to another exponent, you really have to think about how many of what are we talking about. Let me give you an example from last notes. When we said 2 to the 4th, this just means 4 2's being multiplied together. 2 cubed to the 4th, though, we have to ask, what do we have 4 of here? Well, here we have 4 of what's inside of parentheses. We have 4 sets of 2 to the third. So we have 2 to the third here, 2 to the third here, 2 to the third here, and 2 to the third here. And because it's to the 4th power, we know they're all just being multiplied. So this is 2 cubed times 2 cubed times 2 cubed times 2 cubed. Well, hold on a second. We know how to represent 2 cubed as well. Each one of those we can represent as 3 2's. 2 times 2 times 2, 2 times 2 times 2, 2 times 2 times 2, and 2 times 2 times 2. So realistically, how many 2's are we actually looking at? If you counted up all the 2's, you would see that there are 12 of them. 2 to the 3 to the 4th is the same as 2 to the 12th power. How do we figure that out? Surely we don't want to have to make this tree diagram every single time. That's very tedious, especially with higher powers. Imagine doing 2 to the 30th to the 40th. It would take you a year. Instead, let's try to figure out what the rule is. How do numbers 3 and 4 interact to get 12? If you guess that they multiply, you are correct. 2 to the third raised to the 4th is the exact same as 2 to the 3 times 4 power, which brings our answer 2 to the 12th. This is a really nice way of simplifying things, because you might have some parentheses separating you from another exponent. The rule is, if something to a power is already taken to another power, we multiply it. But hang on a second. What do we think about the rule if we had something like this instead? 5 in parentheses raised to the, we'll say, 4th power. Well, normally, if this was to another exponent, we would multiply it. Since 5 doesn't have an exponent, we can just sort of think of it as being gifted this 4, turning it into just 5 to the 4th. Another way to think about it, if you want to stick with this multiplication analogy, is this. 5 raised to the 4th power can always be rewritten as 5 to the 1st to the 4th. Because how many 5's are in here? Just the 1. 5 to the 1st power to the 4th power, we would multiply 1 and 4 and get 5 to the 4th. All right. With these next 2 rules, we have something a little bit interesting that happens. these next two rules are kind of the same rule. I don't like the fact that we separate them into two different ones. I like to combine their ideas. Before we jump into them, I want to ask you this. Let's say we had a problem like this. 3 quantity x plus 2. How would we simplify an expression like this normally? This doesn't have anything to deal with exponents, I mean just in general. Well, you may recall that when we have a number outside of parentheses, and multiple things inside of those parentheses, we distribute 3 times x and 3 times 2, giving us 3x plus 3 times 2, or 3x plus 6. Well, I wonder, can we apply this to exponents as well? For instance, let's say we had the following. Let's say we had 4x inside of parentheses and a square on the outside. Well, normally we know that our rule is we would multiply any exponents. But what exponents do we multiply? Especially if we don't have any in here. Well, we can think about this as being 4 to the first, this being x to the first if you really want to. This 2 would have to multiply with both of these 1's. In other words, we treat exponents kind of the same way we treat a number outside of parentheses. We distribute them. So this 2 is going to go on to our x, and the second power is also going to go on to this 4. This is 4 squared, x squared. And what is 4 squared? 4 times 4, we know that's 16. So this is 16x squared. The rule is, if you have an exponent outside of parentheses, you can distribute it to everything inside of parentheses. Let me give you a couple of tougher ones here. What if I had something like this instead? X squared divided by 3, all that raised to the third power. Uh-oh. We've got some weirdness going on here. But the rules, I should say, are the same. We want to distribute this third exponent to everything in the parentheses. And if we have an exponent raised to another exponent, it means that we multiply the exponents. So what this really becomes is the 3 goes onto here, and 3 becomes an exponent of this too. This is x squared to the third divided by 3 to the third. Well, we don't like this totem pole of exponents. What can we do when it's an exponent to another exponent? We multiply them. 2 times 3 is 6. This is x to the 6th on top. And what is 3 cubed? 3 times 3 times 3. It's 27. Our answer is x to the 6th over 27. There is another type of problem I'm going to give you, and this is the toughest type of problem that you might see. So bear with me. What if I gave you something like this? Let's say negative 2x cubed y to the 4th raised to the 5th power. Okay, now there's a lot to deal with. Here's what I want you to do. First off, don't put so much emphasis on getting this question correct. Second off, I apologize, everyone. It would be much better to make this into the 6th power. Just a quick fix. The second thing is, do as much as you can. If you think you know a way of doing it, try it out. But be very cautious. This 6 has to go on to everything. Pause the video here and see what you get. Hopefully at this point you've had a chance to pause the video. Let's talk about this one. Our 6th power, has to go on to everything. It's like Frank's Red Hot. I put that on everything. So it goes on y to the fourth. It goes on x cubed. It even goes on r2. But there's one thing that didn't get the sixth power, and this is the challenge. As weird as it sounds, we also put it on this negative. Now, Mr. Strager, we can't put an exponent on a negative. There's no number there. You sure about that? Let's write this whole expression inside of parentheses out, except we'll write it as a bunch of things being multiplied together. For instance, we know that y to the fourth is at the end, and we're multiplying it by x cubed, and we're multiplying it by 2. How can we write negative 2 as two numbers being multiplied? We can write it as negative 1 times 2. Yeah, there's a secret hidden negative 1 in there. That's why this problem is so tricky. There's a secret hidden negative 1. So, when we put the sixth power on everything, this turns into negative 1 to the sixth times 2 to the sixth times x cubed to the sixth times y to the fourth to the sixth. What is negative 1 to the sixth power? This is a little bit of a tricky question to ask. You could just put it in your calculator, but let me give you a tip that will help us out a little bit later. Negative 1 to the first power is just negative 1. There's one negative. But how many negatives are being multiplied together, if it's negative 1 to the second power? Well, it's a negative times a negative. What's a negative times a negative? A positive, so it would be positive 1. What about negative 1 to the third power? What's a negative times a negative times a negative? We already know that a negative times a negative is a positive. If we times a positive, these two negatives, by another negative, it stays negative. There's a rule we can follow here, and it follows this pattern all the way up. To the fourth power would be 4 negatives being multiplied together. Well, these two negatives make a positive, these two negatives make a positive, you end up with a positive. The rule is, if you have a negative number being taken to an even exponent, it becomes positive. If it's taken to an odd exponent, it stays negative. Sort of interesting trick to remember. So negative 1 to the sixth power is even, this turns into just positive 1. 1 times 2 to the sixth power is a little bit tougher to find, but not that much tougher. If you think about 2 times 2 times 2 times 2 times 2 times 2, you'll find we end up actually getting a pretty significant number here. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 again is 64. X cubed to the sixth we can simplify because we have something to the third power being taken to the sixth power, so we multiply them. This is x to the 18th. Finally, y to the fourth to the sixth can be interpreted as y to whatever 4 times 6 is. That's 24. When we put this all together, 1 times 64 is just 64, so we can almost pretend like the 1 never existed. Your answer is 64, x to the 18th, y to the 24th. We've actually just talked about the last two rules without really talking about it. The first rule is called the power of a product property, and it deals with when a whole bunch of things in parentheses are being multiplied, like this one. The rule is you put the outside exponent onto everything inside. But the power of a quotient property, the next one, is not much different. It says that when things are divided, the same thing happens. You put the outside exponent onto everything. Like in this problem we did up here. So it turns out these are just the same rule talked about in two different situations. That's why I say I dislike these are two separate rules. They both talk about the same thing. Bring an exponent outside of parentheses into the parentheses. All right. Last set of notes we did we talked a lot about the questions that have red circles around them. This time I want you to test your knowledge out. I want you to try out problem number 18 for yourself. Problem number 19, remember to simplify any negative exponents we get. Problem number 23. And the challenge problem is problem number 21. I want you to try out these 4 problems for yourself. And in a minute, we'll come back and you'll be able to check your answers. Try these out, and we'll come back in a moment. All right, y'all. As we can see, problem number 18, we end up getting q to the 15th because we just multiply these exponents together. Number 19 is similar, but there is another step to it. Once we get a to the negative 8th, because negative 4 times 2 is negative 8, we do not like negative exponents. So to simplify, we have to do our flip from last notes. Number 23 has a similar problem. We distribute our negative 3 to everything on top and bottom, giving us 4 to the negative third over x to the negative third. Well, 4 to the negative third we'll have to put on bottom to make positive. X to the negative third we can put on top. So they kind of swap places here. Then 4 to the third power is 64. So this is x cubed over 64. For problem 21, did you remember the negative sign? Because negative 1 to the 4th power is just 1. 4 to the 4th power is 256. And d to the 4th power is d to the 4th. So we get 256 d to the 4th. All right, everyone. Hopefully these notes helped you out a little bit. If you have any questions, as always, feel free to email me. But for now, have a fantastic rest of your day.